Okay, I'm recording now. So this is lesson number 33, Hyperbolas part 1. Good morning, everyone. Thought I'd start with the brain teaser here. So was anyone able to figure it out? I'll pause the recording, give you a second. I hope that you all are doing well. Here's where we're at right now on the calendar. So this was last week. We're in the 6 weeks. This was last week. We talked about ellipses, part 1 and 2. By the way, some of y'all I still haven't received the practice from. You know who you are. If that is you, make sure that you do submit that because I'm waiting on sending the answers so everybody can check their work until I have everyone. So make sure you get that in for me. So we didn't have class yesterday. I had a meeting about link crew stuff, and so we are moving this Hyperbolas part 1 to here. That's what we're doing today, Hyperbolas part 1. And then Hyperbolas part 2 to Wednesday. And then this one we shouldn't need a class for. We just do practice. So I just wanted us to mix up ellipses and hyperbolas and be able to know when to use what, because they're similar formulas, but they're slightly different. So we won't have a class for this Thursday. So it'll be 2 classes this week. One will be today, Hyperbolas part 1, and then Wednesday will be Hyperbolas part 2. And I've already posted both the notes and the practice on Google Classroom for you to follow along and for you to do the practice on your own pace. And everything we do Friday, and I'll have Zoom office hours on Friday if you have any questions, okay? I send a message on Remind, and if you haven't seen it in the news or if you didn't get to read my Remind message, it is official that schools are closed for the state of Texas, public, private, charter, every school, for the rest of the semester. And I just wanted to get your thoughts. How are we feeling about that? As we maybe mixed feelings. Some of y'all may be really enjoying the time at home and getting a break. Some of y'all may be really missing friends. Some of y'all may have expected to come back. Some of y'all may have been expecting not to come back. Just as we process that, I'd like to hear from you how you're feeling, given now that it is official that that is the case. We have 4 goals. So we will learn math, build character, never give up, and ask why. All right, let's jump into it. So as a refresher, last week we talked about ellipses, and we talked about the 2 different equations. This one right here, which is the equation of a horizontal ellipse because the a is under the x. We talked about vertical equation for an ellipse, which is where the a is under the y. We talked about foci, and we talked about the relationship between a, b, and c being c squared equals a squared minus b squared. That was what we talked about with ellipses. And we also talked about eccentricity, which was c over a, which determines how stretched or how circular the ellipse is, right? And then we talked about also some vocabulary. This is just to recap. The a, we talked about the major axis, which is this. We talked about the a, which is half of the major axis. We talked about the minor axis, which is this whole thing. And we talked about the b, which is half of the minor axis. And we talked about the c, which is the distance from the center to the focus. So just a reminder about those. There's going to be some similar things and some slight different things about hyperbolas. So just want to make sure we know our ellipse kind of piece as well before we get into hyperbolas. And the last piece was for the conic section. If you look at the top right, it is when the plane intersects one cone at a slant, in which you get that ellipse conic section. So now what we're talking about is the hyperbola. And remember, the conic section for the hyperbola is going to be when the plane intersects both parts of the cone, the top and the bottom. That is when it forms a hyperbola. Okay, so let's start with some vocabulary first for hyperbola. Okay, so for so first, the kind of relationship between the focuses. So for the focus of an ellipse, the foci are inside of the ellipse, and the distance, if you just pick a random point, if you remember, and you call this D1, you measure that, and you measure this D2, and you add them up, they're going to be equal to another random point that you pick, like say here, and you get D3 and D4. If you add those up, those distances will be equal, right? That was a relationship between the foci and the ellipse. For the hyperbola, however, it's slightly different. In this case, for the hyperbola, the foci are going to be on the outside of the hyperbola, and everything is with relationship to the foci here. And in that case, if we had a ruler, we would measure, but what's going to happen here is if you pick this random point on one side of the one part of the hyperbola, and you measure that distance and you call that D1, and then you measure this distance and you call that D2, okay? And let's say you pick another random point over here, and you measure that distance from this focus to that and call that D3, and you measure this distance and call that D4. In this case, the relationship between those distances is that D1 minus D2 equals D3 minus D4. So for a hyperbola, it's not that the adding of the distances together will be constant, it's the subtracting of the two distances together that will be constant for any part of the hyperbola. That is where part of the formula that we're going to talk about here in a minute comes. So one slight difference first so far is that the focuses are not inside the ellipse. For a hyperbola, it is outside. So that's the first thing. Second thing is you're going to be subtracting the two distances. And if you subtract the two distances from any points along the hyperbola, they will be equivalent. So that's the first slight difference with an ellipse and a hyperbola, okay? So looking at this one on the left would be considered a horizontal hyperbola, okay? So this is horizontal, and this is considered a vertical hyperbola. All right, center is going to be center in the middle. So this is our center right here. So if you think about, this is the middle of, if you think about this as a parabola, this is the middle of it, right? So it's the middle of those two. So that would be 1, 2, 3, comma, -2. And you would still consider the center will still be H and K. It's like that for any conic section. The vertices are going to be these here. Okay, the middle. Those are our vertices. So 0, -2. And 1, 2, 3, 4, 5, 6, comma, negative 6, -2. Those are the vertices. Okay, so our center is in the middle. The vertices are the two middle points. Then we have the A. The A is similar. It is the distance from the center to the vertices. So that is still remains the same. That is the A, distance from the center to the vertex. And so that would be 3 in this case. Okay. Now you don't have a major axis. It's not called a major axis, at least. It's called a transverse axis. Okay. So the transverse axis is this one. Similar, twice the A, but instead of being called a major axis, it's transverse axis for a hyperbola. So that transverse axis is double the A, so that'll be 6. So you can write off to the side if it helps you, similar to major axis. It's just called transverse axis. The transverse axis will always connect the two vertices, and it will always pass through the center, okay? Now C. C is the distance from the center to the foci, right? Similar here, distance from the center to the foci. We don't know where the foci is exactly. We'll learn how to find that later. So I'm just gonna place a foci somewhere and just assume that that is where it is. Just keep in mind it is not accurate. We do know, however, that the foci have to be on the outside of the hyperbola, and we know it has to lie on the same line as the transverse axis. So the foci are not going to be here, right? They're on the outside. So I'm just going to say it's right here. Okay. This is just an estimation. We'll learn how to find where exactly that is. All right. So the C would be the distance from here to here. That'd be the C. 1, 2, 3, 4, 5. Okay. Let me pause and see if there are any questions thus far. If you have a question, you can ask it via the chat or unmute yourself. If you're good, you can put a thumbs up or say no, we're good. I don't want to make sure I'm not going too fast. Okay, I have a question then. What is something different that we should notice about the C and the A of the hyperbola versus the C and the A of an ellipse?
The A is smaller than the C.
In a hyperbola, the A is smaller than the C. Okay, and what about an ellipse?
The A is bigger than the C.
Very good. That's important to know. In an ellipse, because of foci are in the middle, this would be our A, right? And this would be our C. In a hyperbola, however, because the foci are on the outside, the C, as you can see here, is bigger than the A. That is always going to be the case, okay? Where in an ellipse, the A is bigger than the C. In a hyperbola, the C is bigger than the A. Now, to extend that thinking a little bit further, what does that tell us about the eccentricity? What does that tell us about the eccentricity? What does that tell us about the value of the eccentricity of an ellipse versus a hyperbola? So the hyperbola is always going to be greater than 1. Very good. So if you think about that, because we said for the ellipse, because the C is smaller than A, like let's say the C was 5 and the A was 10, remember we said the ellipse eccentricity always is going to be between 0 and 1. It's not going to be 0 because that's a circle. It's not going to be 1 because that's a line. It's always going to be between 0 and 1 for an ellipse. For a hyperbola, because the C is bigger than the A now, let's say that this C, let's use this example, the C was 5 and the A was 3, that is now going to be bigger than 1. So if you purely have eccentricity and the eccentricity is bigger than 1, it's a hyperbola. If it's between 0 and 1, it's a ellipse. If it's 0 exactly, then it's a circle. Those are kind of how they relate to the conic sections, okay? All right. Now let's talk about the equation. So if we look at the equation here, this is the equation of a horizontal hyperbola. Now, it's important to note that there are very slight and minor differences between an ellipse and a hyperbola. So you have to be careful when you're writing the equations. It's easy to get confused. One thing that we notice here is that this one has a minus for a hyperbola instead of a plus. That's the first difference. And the reason for that has to do with what I said at the beginning. For an ellipse, it's the addition of the distance from the focus to the ends. But for a hyperbola, it's the subtraction of the distances that give you a constant value. So that's why this one has a minus, okay? It's the first thing to note. Hyperbola will always have a minus. Now, this is the equation for a horizontal hyperbola. So we notice the A squared is below the X. That's normal. That's what we're used to, okay? The difference, however, for a vertical, this is the equation of a vertical over here. What we notice is still minus, but the A squared doesn't move. The A squared stays in that first term. And it is below the Y, similar to how we talked about that with ellipse, because it is vertical. But you have to note here that this is not h. So you're not going to put, like, let's say you were using this 3 comma negative 2, you're not going to put 3 and then negative 2 here. You have to be careful that when you switch the order, then for k, you have to put the y value of the center, not the x value of the center. And the ellipse was a plus, so you could switch the order and it didn't matter. But because this one is a minus, you can't put this one first. Like, you can't say x minus h squared over b squared minus y minus k squared over a squared. You can't switch the order like you could with an ellipse, because addition is the same. The reason for that is because if you do 3 plus 2, that equals 5. If you switch the order and do 2 plus 3, that equals 5. That's still the same, right? But if you're subtracting and you say 5 minus 2 equals 3, but then you switch the order and you say 2 minus 5, that does not equal the same thing, right? And so we can't switch the order there. We're going to remember that we're always going to keep the a squared under. So in the equation, the a squared is always first. If it is vertical, then the a squared is under the y, like in this case. If it is horizontal, then the a squared is under the x. But we can't interchange the order. Let me erase this. I'm leaving stray marks all over. I remember y'all mentioned that bothered some of y'all in class. It's harder on here to erase. Okay. So let's talk about the vertical hyperbola. So similar vocabulary. So here's the center here, 3 comma negative 2. That's our center. Vertices, similar. It just now is vertical. So we have that and that. So what's that? 3 comma 1 and 3 comma negative 5. A, the distance from the center to the vertex. So that's 1, 2, 3. Transverse axis is distance from vertex to vertex. This one will have a vertical transverse axis, double the A, that'll be 6. And we don't have our C, we're just assuming, I'm just saying, let's say that it's here. It has to be on the outside, but we'll talk about how to get the exact C later. So let's just say that's the C, 3 comma 1, 2, 3. No, I'm sorry. C is the distance. So C is the distance from the center to the focus there. So this would be the C. 1, 2, 3, 4, 5. Okay. Any questions thus far about the hyperbola? So we talked about center, the transverse axis, the A, the C, the slight difference in the equation. What are we missing here that we haven't talked about, that we have with an ellipse? One part of the formula. Yeah, Hugo, he sent it in the chat. The B. Yeah, we haven't talked about the B. So where is the B? So let's look at that. Okay. So with every hyperbola, you have asymptotes. Okay, slant asymptotes. So if you look back over here, these actually have asymptotes right here, diagonal, and an asymptote here. So every hyperbola is going to have 2 asymptotes, one positive and one negative. So the B comes from the relationship between different parts of the hyperbola and the asymptotes, okay? So let's look at this one that we have on the left here. So the transverse axis here is just, that's our transverse axis, right? 1, 2, 3, 4, 5, 6, 12 is a distance. And the A here is from here to here, half of that, 6, right? So we know that. Now, to find the B and to find the, what we call the conjugate axis, what you would do is you would first, so all we know, right, we're pretend all of these dashed lines are not there. And all we know right now is is this right here, the transverse axis. So you would need the asymptotes first. So you have these two diagonal asymptotes. So you would use those. You would find that, which we'll talk about next class. How do you find the asymptotes? But so we have the asymptotes, and what you would do is you would take your pencil, and you would go from the vertex here up until you hit the asymptote. So you go from the vertex up until you hit the asymptote, and here I hit the asymptote. Okay, and you would go from the vertex down until you hit the asymptote. You would do the same thing on the left side. You would go from the vertex up until you hit the asymptote, and you'll go from the vertex down until you hit the asymptote. And so what that does for you when you go from the vertex up to the asymptote and from the vertex down to the asymptote, then you can connect those two. You can connect this with that. And you can connect this with that. And it creates a little box. And your B is going to be the distance from the center. So if you always think about it, the major axis in the ellipse was the horizontal, if it's horizontal, and then the minor axis crossed vertically, right? It was like perpendicular to each other. So it's similar here. We have our major axis here, and so our minor axis, or not minor axis, sorry, we have transverse axis there. So what we call our conjugate axis, which is similar to the minor axis, is this one right here. So from that top of that rectangle to the bottom of the rectangle, that would be called the conjugate axis, which in this case, the distance is 4, okay? And the B is, just like with the other one, half the distance. So the B is that right there, which is 2, okay? Now, you don't always have to draw the box if you're just trying to find the B, because if you notice this, it's going to be the same distance as this, right? And so you could just look at when you go from the vertex up and you hit the asymptote, you could say that's the same distance of what you have over here. You don't have to draw the whole box, but just so you can see where you find the conjugate axis, okay? So C. So if you think about the C, we need to look at the relationship in the formula, okay? It is slightly different. So there's kind of things that are very minor differences. So if you look at the equation for a hyperbola, we'll get to asymptotes later. The A, B, and C relationships is C squared equals A squared plus B squared. For an ellipse, it was C squared equals A squared minus B squared. So you have to take note of that small difference there. The reason why that is because from here to here is our A, right? From here to here, we just said that was B, because it's the same as this, right? You're hitting the asymptote. That's B. The C is the distance from here to your focus out here. That is your C. If you were to take a ruler and you were to measure that distance, and then you were to turn that around slightly, it would be equivalent to this distance right here, the diagonal. They're always going to be equal. And so that's why it's A squared plus B squared equals C squared, because this is a right triangle right here. And this squared plus this squared is going to equal that squared. So that is going to be the relationship between A, B, and C always, okay? So if you had this A and you had this B, and you were trying to write the equation, it'd be C squared equals A squared plus B squared. So you would use that and you would get C squared equals 6 squared plus 2 squared. So it'd be C squared equals 36 plus 4. So C squared equals 40. And so your C would be the square root of 40. And if you got that as a decimal, it would be 6 point something. So if you were trying to find where your focus was of the hyperbola above, you'll be going from here, from the center, 1, 2, 3, 4, 5, 6. This is 6 right here. You'll go 6 point something. So that means your focus is somewhere around here, somewhere around there. And then there'll be another one somewhere around here. You could get the exact value if you square root of 40. So that's kind of how you would find that. Okay. Any questions? Okay, cool. So this is just a kind of recap of all the features. So we have the A, which is the distance from the center to the vertex. We have the C, which is the distance from the center to the focus, which is always on the outside. We have the covertex. I didn't talk about the covertex, but these are the covertexes, which are on the top and bottom of the conjugate axis. This is our conjugate axis. This is our transverse axis. Then we have two diagonal asymptotes. And then the equation for hyperbola is minus and minus. And the formula for C is C squared equals A squared plus B squared. Okay? So there's very minor differences with the hyperbolas that you want to be careful of. Okay? So we'll skip that part because we just talked about that. Okay, so let's actually try a problem. Let's do two problems together. So we'll read this one. It says, find the equation of a hyperbola whose vertices are -1 and 1 and -1 and 7. And the foci are -1 and 8 and -1 and -2. So first I would just draw this on the graph. So -1 and 1 and -1 and 7 are the vertices. Just from the vertices, we will be able to find three things about this hyperbola. Give me one of them, someone. What's one thing we can find just based off of the vertices here? We can find three total things. So what's one of the things that we can find just from the vertices?
It's a vertical hyperbola.
Okay, good. We know it's a vertical because the vertices tell us that it's going to look something like that. Okay, so vertical. Someone else give me something else we can find about it.
The center.
Okay, good. The center is going to be in between the two vertices. So our center is right here. -1, 4. What else? One more thing we can find from the vertices. We know
A.
yes, we know the A because the A is the distance from the center to the vertex. So the A would be 3. So from the vertices, we know those things. So just from that, really the only other thing we need is what? To write the equation. We know it's vertical, we know the center, we know the A. We're only missing one more thing.
B.
B, right? So we need to use the foci to kind of help us find the B. So we'll go ahead and write the foci. -1, 8. -1, -2. Wait. Something looks off. Hold on. Okay, I might have made a typo here because there's no way that this distance has to be equivalent to this distance, and it's not. So I think we're gonna have to change this value to 0. Okay, so that we move this here because it has to be the same. Okay, because our parabola is like connecting with the vertexes, something like this, right? It's just a rough sketch. And so these vertices have to be equal distance from the center. So we're just going to change that to 0. I might have made a typo there. So that will help us to find the C, right? The C is the distance from the center to the vertex. So that would be 4. And then we just needed a B, right? And so then we can use the equation C squared equals A squared plus B squared to find the C. So it'd be 4 squared equals 3 squared plus b squared. Let me change the color. I'm not sure if y'all can see that well. And then we would solve that. 16 equals 9 plus b squared. Subtract 9. 7 equals b squared. So the square root is, we're going to leave that as a radical square root of 7. So that will be the distance from here out will be the square root of 7 to the box that's created from the asymptotes. Okay, so that's enough information. So then we want to write the equation. So are we using the one on the left or the one on the right here if it's vertical? So are we using the equation on the right or the equation on the left?
The one on the right.
The one on the right, yes, because the a is under the y, right? So y minus, be careful here, this is k, not h, so it is 4 squared over a squared. A is 3. 3 squared is 9. Minus x minus h. H is negative 1. We're going to change it to plus 1. 2 negatives make a positive. Over b squared. Our b is square root of 7. But if we square root of 7, the square root and the square root cancel out. So we just have 7. And that equals 1. So that is the equation of our hyperbola. And we could check that if we wanted to by graphing and kind of comparing it with the one that we have. So awesome. All right, let's try one more. How about y'all try? Yeah, y'all try this one, and we'll talk about it after. I'll give you some time.
B squared.
Okay.
Subtract 25. We equal 39. Then the square root of 39.
Okay.
And then you can set up the equation, which would be the first one on the screen. So it would be x squared, since the h would be 0, just cancel out, over 25 minus y squared over 39 is equal to 1.
All right. Awesome. Very good. Hopefully, is that what the rest of y'all got? Or do you have any questions on that part so far? See some thumbs up. Awesome. Awesome. Kelly, you get a virtual ticket. All right. So that is kind of eccentricity, some of the basics of hyperbola. Next class, we'll talk about slant asymptotes. But before we do that, just one quick thing to know, because this comes up on the practice. Let's say that instead of giving you the eccentricity like that, let's say that you drew it, or what do we have for this one? We had the a of, was 5, right? So let's say you draw the hyperbola, you get an a of 5. But then it says eccentricity is let's say it says eccentricity is 10. Okay. No, let's not do 10. Let's say C over A. Let's say it says eccentricity is 7 over 10. Okay. The equation for eccentricity is C over A, right? And it's saying that the eccentricity is 7 over 10. You want to be careful there to not think that you did something wrong because your A that you got from the graph, like when you graphed it over here, your A that you got from the graph was 5, but then over here it says the eccentricity is 7 over 10. You want to be careful to say, okay, maybe I did something wrong. My A is supposed to be 10 because it's C over A is 7 over 10. That is just a simplified or expanded version of the fraction. Okay, so what I like to do to set it up, I put E equals C over A. I put what the eccentricity is. Then I put equals, and I have the information I got from the graph. So from the graph, we got 5. So on the bottom, I'm going to put 5. Okay. So that means that this was just after it was multiplied by 2. So you kind of find the ratio. So you go from this to this by multiplying by 2. So then you need to go from this to this by multiplying by 2. So that means your C is 3.5. So you want to just be careful because a lot of times your eccentricity might be a simplified version of the fraction, but your actual A from the graph is a different value than the kind of what it looks like it is from the eccentricity. So when that is the case, you want to set up a proportion like that. Just be careful that there's a couple of questions like that that come up on the practice. Okay. All right. So that being said, we moved this. I should change this. This is here. This is here. Tomorrow we'll do hyperbolas part 2, 10 o'clock. The practice is posted on Google Classroom. It'll be helpful if you kind of do it before tomorrow's lesson so you kind of get some practice on hyperbolas, but it's not due until Friday. Any last minute questions?